We continue our video series dedicated to energy storage technologies. And today we will talk about unconventional approaches to solving this problem, where energy is stored not in the form of chemical bonds, as in traditional galvanic batteries, but in other, sometimes quite unexpected forms. Most of the technologies we will discuss today are not intended for mobile electronics or electric transport. They are mainly developed for creating large stationary energy storage systems, without which the energy revolution, on the verge of which we stand today, would be impossible. Yes, indeed. Today, for the first time in human history, we are finally close to moving away from burning hydrocarbon fuel as the primary energy source. And first and foremost, this has become possible thanks to the impressive progress made by solar energy in recent years. Just 10 years ago, I was personally quite skeptical about this industry, seeing it rather as an expensive toy for wealthy countries. However, today, under the pressure of facts, I am forced to reconsider my opinion. Since the beginning of the 21st century, the cost of solar electricity has dropped by approximately 80%, reaching an average of 6 cents per kilowatt hour, while the cost of 1 kilowatt hour generated from burning hydrocarbon fuel is about 5 cents. Simply put, the costs of solar and hydrocarbon energy are now comparable, and if current trends continue, solar power will surpass hydrocarbon-based energy, becoming the cheaper source. By the way, perhaps we should make a separate video about solar panels, how they work, and how scientists and engineers plan to make them even better, cheaper, and more efficient in the future. If you'd be interested in such a video, let us know in the comments. However, no matter how much we improve solar panels, they will always have several significant drawbacks. The key one being their strong dependence on external conditions. Solar panels cannot operate at night and have reduced efficiency in cloudy weather. This is precisely why an energy system based on solar power requires powerful battery stations, which charge during peak electricity production periods and release energy into the grid when production decreases, thereby balancing the energy system. By the way, other non-hydrocarbon energy sources also require similar balancers. Nuclear power plants, for instance, while independent of external conditions and generating electricity steadily, do so too steadily, with almost no ability to adjust power output as needed. Meanwhile, electricity consumption fluctuates depending on the time of day of the week, season, and so on. Simply put, for the energy revolution to become a reality, we need batteries. Lots of batteries. According to current estimates, in order to completely abandon hydrocarbon fuel on a global scale, we need to build battery storage systems with a total capacity of at least 17 to 20 terawatt hours. And we must keep in mind that the cost of today's dominant lithium-ion batteries in the energy sector is about $100 to $150 per kilowatt hour, meaning that building battery stations would require an investment of approximately $2 to $3 trillion. And that, I stress, is the bare minimum. And that's not even mentioning that lithium-ion batteries have a rather limited lifespan, rarely exceeding 10 years, even in industrial systems, after which they need replacement. As they are used, batteries degrade fairly quickly, losing capacity. So in reality, maintaining a global energy storage system would require very substantial ongoing costs. In short, the lack of reliable and affordable energy storage technologies is the main obstacle to the energy revolution today. And this revolution is necessary, not only because we don't want to harm our environment, but also because our electricity needs are constantly growing, while the Earth's hydrocarbon fuel reserves are finite, as are our capabilities for increasing extraction rates. So it is no surprise that massive efforts are being made to remove this obstacle, and energy storage research is receiving widespread attention. At the same time, we already have a technology, one that has existed for quite a while, that allows us to store large amounts of electricity affordably and reliably. I'm talking about pumped storage power plants. The idea is extremely simple. We have two reservoirs, one located lower than the other. The charging of a pumped storage system is simply pumping water from the lower reservoir to the upper one using electric pumps. Then, when energy needs to be supplied to the grid, we just let the water flow back down under the force of gravity, spinning generators along the way to produce electricity. In this sense, pumped storage plants are a type of so-called gravitational batteries, in which energy is stored as the potential energy of objects in a gravitational field. This technology has been in use since the late 19th century and has proven its effectiveness, primarily in terms of cost per unit of stored energy, which is around $5 per kilowatt hour of available capacity. However, pumped storage power plants also have their drawbacks. The first is that building such a facility requires two suitable reservoirs of sufficient volume located at different elevations, and such conditions are far from universal. What, for example, should Australia do, where water bodies are already scarce? However, in theory, it is possible to raise and lower not just water in Earth's gravitational field, but other things as well. A creative reimagining of the pumped storage concept is the project proposed by Ares, a company named after its advanced rail energy storage technology. As the name suggests, the system consists of several railroad tracks, along which heavy rail cars move, filled with virtually any material. During the charging phase of this giant battery, the cars are moved uphill, and during discharge, they roll back down under the force of gravity, spinning generator rotors to produce electricity. The idea looks quite intriguing, but it has two key drawbacks. First, building such lines still requires elevation differences, which are not available everywhere. The second issue is cost. According to Ares' own estimates, their system costs around $170 per kilowatt hour, which is even higher than lithium-ion batteries. However, this drawback could be partially offset by lifespan. Estimates suggest the system could operate for about 30 years without significant maintenance costs, compared to 5 to 10 years for lithium-ion batteries. But even with this factored in, it still turns out to be, to put it mildly, quite expensive. Another gravity battery concept is offered by Energy Vault. A few years ago, they introduced a widely discussed energy storage project using special towers made of concrete blocks. At the top of the tower, cranes are installed to lift the blocks up when there is excess electricity in the grid. Then, when there is an energy shortage, the crane motors switch to generator mode. The blocks descend under their own weight, generating electricity in the process. The idea was widely discussed a couple of years ago, but was ultimately deemed not very successful. The energy density of such a concrete battery is about 30 watt-hours per kilogram of concrete, meaning that to store 20 terawatt-hours of electricity, we would need around 700 million tons of concrete, costing approximately $17 billion. And that's not even counting cranes, other equipment, or the cost of transporting all of this to the site. Moreover, the concrete blocks would need periodic replacement. Concrete is quite strong, of course, but after numerous lift and drop cycles, the blocks would suffer damage, develop cracks, and so on. Finally, such installations would likely be vulnerable to harsh weather conditions. They would probably be inoperable in strong winds, for instance, or under icy conditions when the blocks become covered in ice, not to mention that storms could potentially damage the towers themselves, which don't appear to be particularly stable structures. In the end, even Energy Vault admitted that the idea was not the best and significantly reworked the concept. In 2024, in Jiangsu Province, China, they built the first operational gravitational energy storage plant for commercial use, called EVRC, which doesn't look much like the concrete towers in the original project. The new gravity battery resembles a 100-meter-tall building, inside which massive blocks are moved more like elevators than cranes. Another key improvement is the construction of the blocks themselves. Instead of concrete, they are simply made of compacted earth, bound together with a small amount of cement. According to Energy Vault, these advancements have reduced the cost of energy storage to around $55 per kilowatt hour, meaning their gravity battery is about 3 times cheaper than a lithium-ion battery of the same capacity. The idea still has plenty of critics, but now that we have the first working installation, not just a prototype, but a real grid-connected gravity battery, all we can do is wait and see how it performs in actual operation. Another approach to energy storage involves batteries that store energy in the form of the internal energy of chemical substances. And you may have encountered this technology in practice if you've ever used so-called salt-based chemical hand warmers, those fascinating devices that remain liquid until you press a metal disc inside, after which the material begins to solidify and heat up. These hand warmers are usually filled with a supersaturated solution of sodium acetate, which, at room temperature, should crystallize, but doesn't due to the absence of crystallization centers. When we bend the metal disc, tiny fractures form on its surface, creating these very crystallization centers, which trigger the process. And since crystallization always releases heat, the hand warmer heats up. After use, the hand warmer can be recharged by placing it in hot water. As the temperature rises, the solubility of sodium acetate increases, and the crystallized substance dissolves again. Essentially, a salt-based hand warmer is a real battery, not an electrical one, but a thermal one. More precisely, a phase-change thermal battery. In industrial phase-change thermal batteries, various substances are used. Glauber's salt, with this chemical formula, is particularly popular. When heated above 32 degrees Celsius, water begins to separate from Glauber's salt crystals, dissolving them and absorbing energy, quite efficiently, at about 50 watt-hours per kilogram. When the temperature drops, the reverse process occurs. Crystallization releases heat in the same 50 watt-hours. As we can see, the specific energy capacity of a Glauber's salt thermal battery is comparable to that of lithium-ion batteries, while its cost is essentially just the price of the material itself, meaning the storage cost of 1 kilowatt-hour is only a few dozen dollars per kilogram. However, this concerns thermal rather than electrical energy. And if we are talking about storing electricity, it must first be converted into heat and then back into electricity during discharge. This leads to energy losses in every charge-discharge cycle. The efficiency of converting heat into electricity rarely exceeds 50%. Losing nearly half the energy is far from ideal, making the prospects of phase-change thermal batteries as electricity storage solutions rather questionable. But they can be used for their intended purpose, as heat storage systems, including for waste heat, which is produced in large quantities by nuclear power plants, for example. In summer, this heat can be stored in phase-change batteries, and in winter, it can be used for heating buildings or warming water. Glauber's salt batteries, with their relatively low operating temperature, are not particularly suitable for this purpose, but other compounds with operating temperatures of 60 to 70 degrees Celsius can be used. Meanwhile, supercooled molten metal batteries operate at temperatures as high as 300 to 500 degrees Celsius. Phase-change thermal batteries are already being gradually implemented in practice. For instance, they are used for water heating as an alternative to conventional boilers, since such systems take up less space while storing enough energy to heat larger volumes of water. Another way to store electricity as internal energy is through systems somewhat misleadingly called cryogenic energy storage, which are often referred to in science media and videos as gas batteries. The working principle is fairly simple. In a discharged state, gas is stored in a large tank. When charging, powerful compressors liquefy the gas and transfer it into smaller, sealed storage containers. During discharge, the gas is allowed to expand back into the large reservoir, and along the way, it spins generators, releasing energy. The advantages of these systems include eco-friendliness, reliability, ease of operation, and excellent scalability, meaning you can easily build a storage system of the desired capacity simply by adjusting the size of the reservoirs. There are several variations of this technology depending on the type of gas used. For example, ordinary air can be used. It's free and available everywhere. With this approach, the estimated storage cost per kilowatt-hour of electricity could be around $70. The problem is that at atmospheric pressure, air only liquefies at -200 degrees Celsius. meaning you either have to compress it extremely hard to condense it at room temperature or cool it further. At the same time, compressing and especially liquefying air releases a large amount of heat, which is not very useful. And conversely, when the gas evaporates during discharge, it cools down significantly. All this leads to a relatively low efficiency of such systems, around 40%. On the other hand, instead of air, we can use carbon dioxide, which becomes a liquid at just 64 atmospheres, even at room temperature. This avoids unnecessary losses and increases system efficiency to about 70%, but it slightly raises installation costs due to the price of carbon dioxide itself. As a result, the cost per kilowatt hour of stored energy increases to $100 to $150, nearly the same as lithium-ion batteries. However, enthusiasts of this technology claim that gas batteries will be more cost-effective due to their long lifespan, around 50 years or more. And as the technology scales up, storage costs could drop to 50 to 70 per kilowatt hour. Gas batteries are already in practical use. Since 2018, a 15 megawatt hours installation by Highview Power has been operating in Manchester, UK. While in 2024, Energy Dome built a 200 megawatt hour CO2-based storage facility on Sardinia Island. One of the most controversial, and at the same time, in my opinion, one of the most intriguing technologies is the so-called Flywheel energy storage. As the name suggests, energy is stored in the form of kinetic energy of a rapidly spinning flywheel inside the system. When charging, an electric motor accelerates the flywheel, and during discharge, the flywheel spins the rotor of a generator, producing electricity. Flywheel batteries have several major advantages. Unlike many other energy storage systems, they are completely unaffected by the number of charge-discharge cycles. Flywheel batteries also offer unmatched flexibility in terms of power output, both during charging and discharging. The input or output power can range from just a few watts to hundreds of kilowatts within the same unit. This allows them to power high-demand devices when needed, while also charging in mere minutes. Additionally, they can instantly switch between charging and discharging modes, making them ideal for systems requiring fast response times. Unfortunately, this is where the advantages end. The first major drawback of flywheel batteries is common to all systems involving mechanical motion. You cannot eliminate friction and its associated energy losses. Due to friction, the flywheel will inevitably slow down, losing energy, much like self-discharge in chemical batteries. To reduce friction, developers employ various tricks, such as placing the flywheel in a vacuum chamber or using magnetic bearings, among other techniques. And these efforts have paid off. Modern flywheel batteries lose no more than 5 to 10% of their energy per month, which is comparable to the self-discharge rate of lithium-ion batteries. However, such efficiency comes at a price, literally. The cost of storing 1 kilowatt hour in a flywheel battery starts at around $500, which is 3 to 5 times higher than lithium-ion batteries, the very ones we're trying to replace, partly due to their high cost. Yes, flywheel battery enthusiasts argue that this is offset by their long lifespan, 25 to 30 years without performance degradation, something lithium-ion batteries cannot match. And that's mostly true. However, other storage technologies we've discussed earlier also offer similar longevity, while costing 10 times less. Additionally, flywheel batteries have a relatively low energy density, typically no more than 50 watt-hours per kilogram, making them inferior to modern electrochemical cells. At this point, I want to elaborate further. The kinetic energy of a flywheel is determined by the square of its angular velocity, multiplied by a quantity known as the moment of inertia. The latter is equal to the mass times the square of the flywheel's radius, multiplied by a shape-dependent coefficient, which, for a solid disk, is 1/2. At first glance, this suggests no fundamental energy storage limit. The faster you spin it, the more energy you store. Unfortunately, it's not that simple. As the flywheel's speed increases, so do inertial forces trying to tear it apart. and at some point, they will succeed. This means that actual energy density is limited by the following equation, where ρ is the material's density and sigma is its tensile strength in pascals. For steel, for example, the density is 7,800 kilograms per meter, and the tensile strength is around 1,000 megapascals. Setting the geometric coefficient to 1, we get a specific energy of about 128,000 joules per kilogram, which translates to only 35 watt-hours per kilogram, compared to 150 watt-hours per kilogram for lithium-ion batteries. But what if we replace steel with stronger, lighter materials like carbon fiber, which has a density of approximately 1,800 kilograms per cubic meter and a tensile strength of 3 megapascals? This would significantly boost capacity to 200 to 300 watt-hours per kilogram, surpassing lithium-ion batteries. This, in turn, makes flywheel storage appealing for electric transport, especially given its short charging time, measured in mere minutes. And if we experiment with nanostructured materials like graphene, which has a tensile strength in the hundreds of gigapascals, the energy density skyrockets to tens of thousands of watt-hours per kilogram, surpassing even hydrocarbon fuels. The problem? We can't yet mass-produce large graphene-based structures, and won't for quite some time. And when we do, they'll be astronomically expensive, at least initially. Still, such materials could find applications where cost isn't a concern, for example in space exploration or the military sector. So I wouldn't write off flywheel batteries just yet, but they will likely be used in mobile energy storage and electric transport rather than stationary energy storage systems. But now we're entering the realm of technologies that, for now, belong more to the realm of science fiction, things we theoretically understand but cannot yet implement. And when it comes to energy storage, there's plenty more to discuss, such as quantum batteries, but we'll cover that in one of our next videos, which will likely be the final episode in our battery series. For now, let's summarize. As of today, we already have several highly promising technologies that could enable long-term storage of large amounts of electricity in the very near future. And these are no longer just ideas or prototypes, they are fully operational systems, already integrated not just in test sites, but in real working power grids. So the key question is, which of these technologies will best stand the test of time and practical use? And that undoubtedly gives us real hope that the long-awaited energy revolution is closer than ever. By the way, in this context, it would also be interesting to discuss what new breakthroughs in energy generation scientists and engineers have in store for us. So if you'd like to see a video on that, let us know in the comments. And for those who enjoyed this video, I'd like to ask for your support by becoming a sponsor here on YouTube or on Patreon or Boosty. A link to the latter should appear on your screen right now. All necessary links will be in the video description. Once again, thank you all, my dear friends, and see you very soon in our next videos.